Welcome back. Our next speaker is Mike G0MJW, who was first licensed in 1983, and he particularly enjoys microwaves, propagation, programming, making things, and of course, DATV. He also designed the club's popular POTY patch antenna project. Today, Mike is going to give us an overview of the KiCAD PCB design tool, and also tips for ordering printed circuit boards. As before, please feel free to ask questions or make comments on BATC messaging or YouTube chat at any time, and please include your first name and your call sign as well. Welcome to CAT23, Mike.
Okay, thank you. Sorry, I'm not seeing you, so I'm working blind here, but hopefully all is working well.
We can see you fine.
Yep, great, excellent. So could we start the slideshow, please? So, no, not the desktop, the slideshow.
There we are. Sorry about that.
Thank
We're
you.
just to explain to everybody at home, we're playing these out for technical reasons so we can get the maximum quality from your PCB design software.
Yeah, exactly. So I'm not doing this as a video stream. I'm doing this as a screen share. And of course, I can't put the image that I'm looking at on the screen share, or it wouldn't work. Anyway, could we go to the next slide, please? There we go. So what I'm trying to do is show you the basics of KiCAD, and then you need to work from yourself. Basically playing with it is the way to learn how to use it, but it can be a bit daunting at first. So what we've got a very, very simple proposed sort of amplifier, which is a Galley 59 Plus. Now, I'm sure people have seen those before. They're simple game blocks, and this screen is really showing the parts from the data sheet and the design. I'm not going to go into RF design here. That's not the point of this talk. But the main things to note are that you have a chip, and it requires several components. It requires DC blocking capacitors. It requires bypass capacitors. It requires a bias resistor, and it requires an RF choke. So could we go on to the next slide, please? So the first thing you do whenever you want to build something is you look to find out what the components are and what the packages are, and ensure that you can actually get hold of them from one of the suppliers. Now, I've used Mouser here, plenty of other suppliers around. The advantages of Mouser and DigiKey websites is that they often have 3D designs or data sheets or footprints for the components. So can we go to the next slide? On the footprint side of things, the only issue you might have with using KiCAD is when you've got a part that doesn't have a specific footprint. So this particular one, the Galley 59 Plus, is in the library, in the KiCAD library. One of the reasons for selecting it, of course. Typically an SMA footprint is in there as well. So that's why I've selected SMAs and the Galley 59. The other point is this is all surface mount. No apologies for that. You can't really get these parts in through hole. So if you want to do something, you're going to have to do it in surface mount, but actually they're pretty big and not too hard to use. So can we go to the next slide? Right. One of the issues with making any RF PCB is you need impedance matched tracks. In our case, 50 ohms input and output. There's a tool within KiCAD for developing those tracks and understanding how wide they have to be, depending on the parameters of the board. Now, in this case, for 1.6 millimeter FR4 PCB material, that's the standard really, you need about a 3 millimeter wide track for 50 ohms. For 0.8 millimeter with PCB, thickness PCB, it's 1.5 millimeters. It's a lot easier to use a 1.5 millimeter track than a 3 millimeter track, for reasons I'll come on to. But if you think about the size of an SMA connector, that's part of the reason. Can we go on to the next slide, please? So here's the schematic. And I've pointed out the 50 ohm lines there that need to be of a particular width. There's not a lot to say really about it. There's an RF input, there's a blocking capacitor, there's the device itself, There's an output block, DC block capacitor, and the RF output. There's an inductor, which is to stop the bias. So the bias comes onto the output pin of the device. It's not got a separate supply voltage. To stop that interfering with the impedance of the line, you need an RF choke. That's what L1 is. The R1 51 ohm resistor, that's so you can run it off an 8-volt supply. You could also run it off a 12-volt supply, but you've got to remember that you'll be dissipating power in that resistor. Some of the devices you can also run off a 5-volt supply directly, but that's not recommended for this one, but you can do that with some of the other devices. Next slide, please. And here's the final result. So this is what I did, I think it was yesterday. I just put that together so you can see what the PCB might look like. And at that point I could say that's the end of the talk, but obviously it's not. So if we can now go to the screen share, I'm going to try and show you how I actually did all of this. Okay, so hopefully you can see that. When you open up KiCAD for the first time and install it, this is the screen you get. And in this screen you can, so I have a project already here, the one that you were just looking at. We're not going to work with that one though, we're going to work with a new one. There are editors for schematic, for symbols, for PCBs, for footprints, a Gerber viewer. So the output of the program is typically a file for PCB manufacture that allows you to look at those files. Various image converters, calculator tools, ways for editing the drawing sheet, and plugins. And the plugins are a very interesting part of KiCAD actually, because it adds extra functionality. Now I have quite a few plugins here, and some of which are going to interfere with this demo, but a particularly useful one is the one that produces the bill of materials, and if we get time I'll show you that in the demonstration. But so what we need to do is we go to File, New Project. So this is called BATC Demo. I'm going to call this Demo 2 for want of a better name, and that's it. We now have a demonstration. There's nothing in it, of course. It's just the three files here, which is generated automatically. And of course it opens it up in another window. So let me move it onto this and get it to fit on the screen. This is what you're presented with when you get into the schematic editor. So the first place to start is the schematic editor. And hopefully you can see that on my screen now. This is all about the hierarchy of the schematics. You can have different pages. I'm going to shut that down because I'm not using different pages. And I can edit the preferences and do the various setups. What I'm going to do on this one is I'm just going to leave it mostly to the defaults. So everything's set to defaults, apart from I'm going to import some settings from the previous project you saw, which is this one, I think. And the reason I'm doing that is hopefully, and you can see it now, actually it didn't do that, is the screen will get a little bit more easy to read. So I'm just trying to make the screen easier to read for you by using a slightly smaller sheet. Now, the first thing you've got to do with any project is give it a name. And in KiCAD, there are a lot of keyboard shortcuts which you need to learn. You can do a lot of things with just using the mouse buttons, but not all of them. And in this case, I want to do something. I have to press the button E, and that brings up page settings. So I want to set this to A5, so that's a smaller one. I want to set an issue date. I want to set a revision. Let's call it 1. Let's call it a title, demo. And you can put all sorts of other things here, like, for example, your call sign or whatever you like. That'll give your sheet, your style sheet, a title and a call sign or a company name or whatever. You can add all sorts of things here if you want to. But let's go now back to the schematic. And this is where I need to reference that schematic. So let me just open that up on my other screen. What I'm trying to do is open up PowerPoint. And the demonstration that you just saw. What I'm trying to do is look at this schematic to remind ourselves what we're trying to do. So you'll need to have that printed out on a piece of paper somewhere so that you can look at it. I'm going to move it to the other screen so you'll see me looking in various directions. Now, the first thing that you need to do is start to add the components. So it will open up various libraries and various things will happen. And hopefully at some point we will get a window coming up which will give us these libraries. There we go. Sorry it took a bit of time, but that's because I think I'm running a lot of things at the same time here. What I need is my Galley 59. So let's see if we can find it. There you go. So these are all the different devices, one of which is a Galley 59. I can now put that somewhere in the schematic window, like so. And that has put that in the schematic. Now there are some other parts I need to add, so I'm going to continue adding parts. The next part I think I'll add is the SMA. And there's actually two of these. And again, look through the library. At some point we will find the connectors. Here we go. Oh yes, coaxial connector, there we go. There are lots of these. I'm going to have to type more of it. Connector coaxial, there we go. Now, what do you notice about that? It's the wrong way round. There are various options you can do. If you right click, mirror vertically, mirror horizontally, we want to mirror horizontally. So there you go, now we've got our connector on the schematic. And actually we want another one. So again, I'll click it and I'll click the same one. So now we've got two connectors, coax 1, coax 2. So your input and your output. And then we need some capacitors. So again, in here, capacitor. And you'll get lots of choices, I'm afraid. Why did that not work? Hang on a second. C. There we go, C. Typed it too many times. So there's an unpolarized capacitor. Now, I don't know if you spotted that something came up about there being a no footprint. We'll come on to that in a minute. Now, another thing you can do, incidentally, is if you do a Control D on the keyboard, you can copy something. It's duplicate, which might be useful if you need two capacitors, say. And actually, we need 3. If you hit the R button, it'll rotate it. So you can see what I'm doing here. I'm starting to build up that schematic. I now want to add something else, a resistor, which comes under R, resistor. And where's that going to go? Well, I think it needs to go roughly around here, so I'm going to need to rotate it again. And I'll put it there. And I also need an inductor, which surprisingly is called L. and I'll put that there. And then the last component we need out of all of these is the DC connector. So I know it's another connector. And we'll go for a generic connector, 2-pin. Doesn't really matter what it is, slightly different to the one I used before. And we'll put that, let's put that around about there. So now we've got all our bits of the circuit together. We need to wire them up, and this is where you need to go into this bit here, and you need to basically start connecting them. But there's one thing missing, and I don't know if anyone's spotted it yet, and it's not a component. So this is how you wire them together. Click on each of the dots, join the dots. Oops, missed that one. That's your schematic. But the thing we're missing here, and that's, by the way, how you join them together. We're missing ground. Now, in KiCAD, power things are treated differently from components. Click on this add a power symbol here, and you're adding the parts. Comes under power, and if you scroll down, hopefully somewhere we'll find ground. That's your standard ground, and you attach that ground to all the things that you want to be grounded. And again, Control D for duplicate. Click on it, Control D. One there. We want one here. We want one here for the capacitor, and we want one here for the power supply. So that's now our schematic done in about 10 minutes. It's not that difficult to do, but there's a lot of things that are missing here, like all of the footprints. So that's what I'm going to talk about next. If I go to, for example, this device, and I hit the E button for edit, it comes up with this menu, and it shows a footprint already associated. That's because that part already exists. So that's okay. We've got a footprint for that one. If I go to the connector though, as you can see, there's nothing there. And that's where we need to click on here again, and another screen will open up. And this is where we do the connectors. And sorry for the slightly difficult to read because I've got all this on a large screen so you can see it on the stream. We need to choose a footprint and connectors. But there's lots of connectors. And down here somewhere is the RF connectors. But there's also connectors via different companies. So these are the libraries that come as standard. You can generate your own libraries. I don't really have time to go into that. But let's go to connectors coaxial. Now we could choose a BNC connector. We could choose MMCX. I'm going to choose SMA, vertical. So double click on that. Okay, we've now got a connector. If I go to the other one, again, same thing, use the same connector. Then we come to capacitors. We need a footprint for the capacitor. Now, again, capacitors are typically using surface mount. 0805 is the typical number. You could theoretically use a through-hole capacitor, but they're getting hard to find, and they also don't work as well RF-wise. So we really do need to start to use capacitors that are SMD. So if I now start typing capacitor here, hopefully, capacitors SMD, it will come up with a huge list of potential capacitors. And you have to look through this until you find the one you want. Now you can actually type in 0805 because that's the package that we're using, and you just start off and it will come with all of these. Now 0603, 0805, that's come up because it's got the 08 there for the imperial, the metric numbering. I will click on this one. The standard 0805 looks like this, but KiCAD has a rather nice one that's designed for hand soldering, so the pads are a little bit bigger. So I'm going to click on that, and there you go, that's there. Now I could go through all these menus again to do all these other ones, but what I'm going to do actually is a shortcut here. You can copy that, because you know you're going to be using the same capacitor here from the parts list, and the footprint, you can just paste it. So that makes it a lot easier. And actually there's a way of bulk editing all of these things if you wanted to. One of the icons at the top, that's bulk editing the fields of all the symbols in the schematic. So that can be a useful way to shortcut all of these things. If we then go to the resistor, we need a footprint for the resistor. Now, again, these will be in here. So resistor, SMD, oops, sorry, that was relay. Resistor SMD. Now, I don't know if you remember from the schematic in the PowerPoint, because I didn't dwell on this, but the power rating of that resistor needs to be about 1/4 watt, which is quite a lot for an 0805. So the solution to that is use a bigger one. And in this case, we're going to use a 2512. So we look through this list until we get to 2512. Again, hand solder. We select that footprint, OK. And then we come on to this one, the inductor. Again, we need to choose a footprint. And it'll be a lot easier when you're doing it because it won't be appearing on 2 screens. But inductor, SMD. Now the particular package for the one that I found in Mouser, which was a 470 nanohenry capacitor with a resonant frequency, a self-resonant frequency in 70 sems, which is what you want for an amplifier that might work around 70 sems, incidentally. That comes in the SMD 1008 package. And there we go. And again, choose the hand solder one. That's that. Now the only component I think we haven't done is this one, the connector. We can select that in the same way. And I'm going to use a Molex connector, and I'm going to use a Molex KK254 connector, and in fact I'm going to use this one, which is a standard 2-pin Molex. Whatever your preferred connector is, use that. And at that point, hopefully, and I will save this now, we've got our schematic more or less done, except for a slight, well, fairly obvious missing thing is we haven't actually got any values. So I'll just fill these in. This one, 1 nanofarad. The resistor, again I'm pressing E incidentally to select this particular thing. What did we say that was? We said that was 51 ohms. I don't actually need to put in any values, but it helps with the bill of materials. This capacitor, 1 nanofarad again. And this capacitor, that was 100 nanofarads. Oops, I selected the wrong thing there. Sorry. There we go, 100 nanofarads. And the inductor, 470 nanohenries. So now we've got our schematic, which hopefully looks rather similar to the one in the slide that I showed at the start. And just to show that, if I can persuade this thing to work, I'll move this over. There we go. I don't know if you can see the similarities here. So we built that circuit. No, I haven't put it there yet. There you go. Can you see it now?
That's fine, Mike. Thank you. Yes, I was just saying we couldn't see it at home. And
yeah, it's a feature of Zoom, isn't it? That unless you actually
the window, but that's fine. No, we can see that fine. So that was the original schematic, and you've recreated that on the KiCAD.
Yes, it's good to get feedback actually, Dave. Thanks for that.
That's all right.
Now, there are various things to check here that you can do. You can, so we can, for example, fill in it automatically labels parts, starting from 1, so R1, R2, C1, C2. You could actually open up a window to do that if you want, and redo them. This, incidentally, this won't appear in your normal, this is a plugin, so ignore that one, but this one is particularly important. This is the footprint assignment tool. Now I did this manually, but you can actually do that in this tool. So all our devices have footprints. You can also generate a bill of materials if you like. But the one I think we want to do is this one. But before we do any of that, I think we need to check whether it's all okay. And we could perform what's called an electrical rules check. Now, in my case, this will come up with some errors. Those errors are all about the simulation. So we can ignore all of these. And in fact, if you want to, you could say, right-click, exclude this violation. Exclude this violation. Ignore all spice. Right, try again. And now it's quite happy. Now, you quite often get this thing about no power. This is again to do with the simulation. Don't worry about it for the moment. It doesn't really matter. There is a way to fix that by using a thing called a power flag, which will come up here. This one. If you put that somewhere around, this just tells KiCAD where the power comes from for when it's doing its electrical checks. But it doesn't really have any bearing on your PCB design. It only really becomes important when you're doing a simulation, which is a bit more advanced. So we got to this stage where we've got a schematic. Now we need to design a PCB. And this takes a long time because you want to make it look nice. But the first thing to do then is to click on this icon here. And let me just bring this into the window. Hopefully that's visible. You have a blank canvas in the PCB design tool. That's all very nice, but the first thing you probably want is your components. So on one of these icons, update PCB with changes made to the schematic. Click on that. And hopefully, there we go. Thank you, Dave. Right, so we're about halfway through, so let me speed up a little bit. Here are all the components that KiCAD has got from the schematic, and put the footprints on. What do you do with them? Well, you just put them somewhere for the moment, because the first thing you're going to need to do is put them on a board. And you've got to think about layout and also how big you want the board to be. And that depends on what sort of box you want to put it in. And you might want mounting holes, you might not. If you wanted a mounting hole, for example, and let me just show you how you do that. You go back to the schematic. Mounting hole is treated just like any other component. Mounting hole with connection, mounting hole without connection. Let's do one without. There you go. We now have a mounting hole. And again, that'll need a footprint. And that footprint, for example, how big do you want your hole to be? M3, for example. So let's double click that. Now we have a mounting hole. Now we probably want, oops, sorry about that. We probably want more than one mounting hole actually. So what you can do, and this is a useful shortcut, is again, Control D to duplicate, Control D to duplicate, Control D to duplicate. If you do the duplication after you've assigned the footprint, and I'll show you on this one, the footprint will already be there. So that's rather useful. So what's happened now, we've added something to our schematic. But that's not reflected in our PCB yet. Click on this icon, update PCB from schematic, close. Here are our 4 mounting holes. So you can switch back and forth between the PCB and the schematic. And that's very useful if, for example, you want to change something. You might want to swap some pins on a component to help with the routing. So here we are. Now the first thing to do is to work out roughly how big it is. And if you want to manufacture a PCB, you need to have a defined rectangle, and it's on a set called edge cuts, a layer called edge cuts. This is part of the Gerber files. If I create this like this, there we go. Sorry. Nice sort of size to choose. Incidentally, I've set the grid to metric. I can show you how to do that, but it's quite simple. Right click. There you go, 40 by 40 millimeter PCB. Now, there are lots of keyboard shortcuts you need to get familiar with. M for move. It would seem logical to put our holes in the corner. As a first start. And then we need to zoom in a bit, I think, because, and you zoom in with a mouse wheel incidentally, because look, they're not quite right, are they? So let's move that. Well, I've set the grid to 0.5 millimeter. So it moves in defined positions. You can set a finer grid, but then it's harder to set something exactly in place. You can also edit it and edit the exact placing if you want. Now J2, this is the output, so I'm going to move and put it here. Now you may be wondering why I'm putting the output where normally you would put the input, but it's to do with the way the device is organized. And I'm going to put other one here. I'm going to put the 2-pin connector there, and then I'm going to look at the device, this one here, and I'm going to move that, and I'm going to, you see these lines that are moving between, those are the connections. Those are what we call the nets, and they say what's connected to what. So I'm going to put that there for the moment because that's about where I think it needs to go. C1, the input capacitor. where's that got to go? Well, that goes with J1. C2, the output capacitor, blocking capacitor, that goes with the output. Let's put it there. The resistor, well, that's going to be somewhere around the DC supply. I'm going to put it somewhere around here. The inductor, I'm going to put it somewhere around here. And the bypass capacitor, I'm going to put it somewhere around here near the connector as well. So that's got all our bits roughly where we might want to see them. How are we doing for time? Okay, we're okay. And now I'm going to zoom in a bit more. And I'm going to move that around. And this is when I now have to start thinking about how I'm going to route this board. And I've also got to bear in mind that we have particular widths of components. So what would be a suitable track width to use? And this doesn't really show up very well, but I'm going to edit the sizes, hopefully. There we go. And I'm going to add some track width. So there's a predefined size which is 1/4 millimeter. It's a bit small, that. I'm going to add a 1 millimeter, and I'm going to add a 1.5 millimeters. So those are the tracks that I think would be about right. And the reason I'm using quite wide tracks is quite often you might actually want to, well, maybe not so much nowadays, but in the old days you might want to hand etch this. So using very fine tracks is not easy. Now I don't know how well they're going to be showing up, these nets on the screen, but these little wires indicate what's connected to what.
I think they're very faint actually to us, so they may be even fainter to everybody at home. But,
yeah.
But that's okay. If everybody at home, if you just look between, for example, as you say, the Galley 59 and straight above it, the Con 01, there's a sort of very fine white or grey line between them.
Yeah.
But I just thought I'd elaborate for people watching at home. Thanks, Mike.
Yeah. So all the nets appear in this table here, and so we have ground, for example, we have what's connected to J1, and we can also turn on and off different parts of the diagram. So I find the thing saying mounting hole, for example, that is a fabrication layer. Don't really need to know that at this stage, so I can turn those off, and it makes the thing look a lot cleaner, so you can see what you're doing. And apologies that you can't actually see these nets, but when we come to wire things up, then it'll become fairly obvious. So let's try doing that. So routing tracks. This tool here allows you to route a track, and I'm going to look at this one here. So I'm going to connect this capacitor up, and now it's highlighted the net, and you can see it's using a very fine net. If I hit the W button, I can use a wider track. There we go. So now we've done that. We've wired that capacitor up to the connector, and that's the bypass capacitor. Now there was also another thing here, which was the resistor. Now then we have the inductor. There you go. Now this is not necessarily the best way to route this, but in the interest of time I'm not going to finesse it. Those are the sort of the DC tracks, apart from then the connection between the inductor and the output of the mod amp. I'm going to turn off the routing. I'm going to go away from the routing of the tracks now and just talk about how we might do the 50 ohm line. Now you may remember I said at the beginning the 50 ohm line is 1.5 millimeters. So for the capacitors, certainly I can just route like so. Oh, but look, That's not going to work, is it? That doesn't look right. So what I need to do is I need to select this capacitor and turn it around. So now it looks a lot better. There we go. Now where is that going to? It's going to pin 3 here. But there are particular requirements for these devices, and if we have, well, we've got a little bit of time. I'm not going to go into great detail here, but
we haven't got too many questions so far, Mike. So
No,
please
okay.
carry on. I think I'll
Yep.
be speaking for everybody and thinking we're intrigued, and we'd like to see you complete
Yeah.
this if you can.
Yeah, so what I'm going to do is I'm going to do a thing called add a filled zone. So that adds a zone, as in a PCB material, that you can draw a graphic. So what I want to do is draw a 50 ohm line. So I want to draw something that looks about 1.5 millimeters wide. Now actually I think that one that I've got here, this one, is not 1.5 millimeters wide. I think that is 1.5 millimeters wide, and there's a little bit of an overlap on the capacitor here, but it doesn't really matter when you do that. But when you come to this one, it'll look a bit strange. So we're going to put in a filled zone, and what I'm going to do is I'm going to start it around here, halfway along the capacitor, and it wants to know, oops, hang on a minute, sorry, I need to choose the layer, the front, let's try again, front copper. Right, what net is it connected to? Well, it's connected to C2 pad 1. I don't want thermal release, I want it to be solid. I'll leave everything else at the default. So now I'm going to draw something that's about 1.5 millimeters.
Mike, could you just briefly tell us what thermal reliefs meant?
Yeah, so thermal reliefs are when you have something that's connected to a big ground plane and you try and solder to it. It's very difficult to get the heat into the soldering iron. So thermal reliefs are little sort of bits. In fact, I can show you it once I've done this. So Anyway, first of all, and I'm just going to make those zones a bit more visible. That zone is now there, and what I can do is I can fill that zone using one of the which is this one here. Oops, no, that's the wrong one. Well, let me go on to doing that. Let's try again. It came up with the instructions here. B. There we go. So the KiCAD shortcut for filling a zone is B, and I don't know if you can see that we've now got that zone, and that looks just like a track, and that's connected those together. But let me zoom out a minute and just show you the thermal reliefs issue, because that's quite an interesting one. What we would have on these PCBs normally is a ground plane on the back, and we do that with a filled zone. So we select the filled zone. We want it on the back copper, and we want to fill up. We want it connected to ground, and I'm going to leave thermal reliefs in, and you'll see what happens. So that goes to there. Draw that in. There we go. Fill that zone up. Now, can you see what's happened here around the SMA connector? We've got little sort of things. They are thermal reliefs. So that's what a thermal relief is.
And that makes it easier to solder in this
Yes.
case, the connector, the metal bit of the SMA. Well, I'm sure we've all tried to solder at some point a giant piece of copper on a piece of on a circuit board, the back of a circuit board, and of course a lot of it takes all the heat away. So that's what those do?
Yes, exactly.
Thank you.
Right, so let's go back to our board design. We've still got a few things we need to do. Incidentally, those do make the ground connections now, which is what we want, so that's fine. Again, like other things, you can copy and paste. But if you do that, you've got to remember that you'll need to edit it because it'll be connected to the wrong thing. I'm just going to copy and paste that, and I'm going to put another one. I'll put it there, and then I'm going to edit it, and I'm going to say what it should be connected to. In this case, it's C1, pad 2, because C1 is there. Now that's going to look a little bit strange, isn't it? Because this capacitor, I think, is also the wrong way around. So we need to rotate it like that.
Is that quite easy what you're doing there, Mike, with the mouse,
Yes,
presumably, to rotate?
yeah.
Okay.
It's not the mouse, it's the keyboard.
Oh, is it?
You hit the button R to rotate right, and I think L to rotate left. Again, you need to learn these things, but it's not too difficult. You can also do it with the mouse. So let me show you. It will come up with, if you right-click on it, it'll come up with this menu for doing things, and you have to select the whole thing.
So like all software, when you get used to it, the shortcuts can help you get around.
And actually, over here we have a selection filter. So if I select nothing, I can't select anything, but I could say just select footprints. And then when I try to select a track, it won't select a track. But if I select footprint, it will select a footprint. And that's really useful because especially when you've got lots of things on top of each other, just connecting the things you want. And in fact, if I turn off zones, for example, I can no longer select these zones, and I've finished with those for the moment. So, that would be good. Now you see I've selected the zone, and it's or I select that zone. What I want to do now, though, is I want to do another track, which would go from here, and I'm going to press the W button to select the wider version. That is my other track. Now, I don't think that's exactly the right width, but we're not going to bother about that now. I'm just going to come on, because of the time, onto the device itself, because that will need connections to ground. And the way, if you look at the data sheet, the way that has to be done is specified. And again, it's another one of these filled zones that I'm going to use here. And this is specific to RF. So what I'm going to do is I'm going to create a big zone covering most of the board on the top copper that is also connected to ground. So I'm going to go here, ground, OK. Now the reason I'm doing this is partly for RF purposes, but really because I want to be able to cool the device. And if you have a large area of PCB copper, it helps to reduce the heat dissipation. So there we are. We've got that zone there now. Let's go back to our device. Now that is all connected, and KiCAD is quite happy with that, but actually we want a via, and if you want to add a via, you use this tool for adding vias. It's always a good idea to have quite a lot of vias in your RF circuit.
Forgive me elaborating on this, Mike, but it's just that a via is a term. If nobody's designed a circuit board, I'm sure everybody will have seen a via, which is really a hole that usually connects the top layer to the bottom with plating through the hole. I just thought I'd explain that for anybody watching this sort of thing for the first time. Thank you.
Yep, that's very useful. Thank you, Dave. And yes, we'll put one here as well. So we've got lots of vias which are connecting top to bottom of the board. So that has now grounded everything. Now we also need a via here for this capacitor, C3, because it's connected to ground. So there we go. Now there's one track missing, which is between L1 and here. I am going to go for the very narrow track here. Oops, sorry about that. The reason I went for a very narrow track is it maximizes the inductance. This device only takes 65 milliamps, so the thickness of the track really doesn't matter. But at that point we've got our PCB designed, so there it is. And we can run a thing called a design rules check. Now that will come up with some errors, and the errors it will come up with are things like logos are off the board. So if you want to move text, you move it, you select it, you move it. So click on it, move it. Don't think we really need to label holes, but and in fact, if you don't want to label a hole, you can edit it. So you can edit the properties and you can make it invisible. So we're not labeling our holes. Now, I don't know if you saw that I accidentally selected the bottom layer there when I clicked. So this is where this selection comes in. If I just want to select text, it makes it a lot easier, because now it won't select, it'll only select the text. I can make that non-visible. There's another one here, hiding. And that just makes your board look a bit nicer. Now you can add text as well, but we've basically got a board here now, and we can do a check. So this window is a design rules checker. Going to run that, run design rules checker. Hurrah, no errors. There you go. So that's our board, all done. Now, one of the nice features of KiCAD is it's got a 3D viewer. So if I click here, click on 3D viewer, it'll open up on the wrong screen again, but let me just pull it over. That gives you a 3D visualization of your PCB. Now, what you notice is the connectors are not in there, and that's because it doesn't have a 3D model of the connector. There's a way to fix that, and I can show that, but it'll probably take a bit more time, and it involves finding a 3D model of the connector and inserting it into the footprint file, and there's a tool to do that.
And if you found that from a library somewhere and you put that into your KiCAD, you wouldn't have to go to find it again, is that right?
Yes, you'd store it in your library. And in fact, at this point, we do the Blue Peter bit, and we shut this down, and we shut all of this down, and we open a recent project. Here's one I did earlier. So there you go. It looks similar. I did a bit of practice. And if you now do a 3D view of that one, you'll see I did actually put the connectors in. But what I want to do is actually move on to the final bit in the last few minutes, which is around what you do with these things. So let's open up the PCB, because you want to order one, yeah? You want to get one from the shop. And you can get plugins for various shops that will actually allow you to do this. But what I generally do is I make some Gerber files. So Gerber files are what you have to send to the PCB house. And the way you do that is plot. Now, the default values of this are generally okay for a lot of the Chinese PCB houses, which is good, because it means you don't have to fiddle around with any of these settings. But in some cases you will, but they'll have information on the website what you need to set here. Now I'm going to put these in a directory, and there isn't a directory there at the moment, so I'm going to create a new folder, and I'm going to call it Gerbers, and I'm going to select that directory, and I'm going to plot the Gerber files. It wants to redo the zones first, which is fair enough, so it'll do that. It's very important that you also click on generate drill files for the holes. So generate a drill file, generate a map file, close, and then close these off. It's now created all the files in the Gerber file, in the Gerber folder. And if you were to go and look at that folder, so let me just, save this. Let me put that down. There is a Gerber viewer here, and the Gerber viewer allows you to look at those files. So you can open Gerber files, and I'm going to have to select. So where do we put it? We put it in here in Gerbers. So we got front copper, sorry, back copper, front copper, edge cuts, solder masks, all these things. So let's look at the front copper. So that's the tracks basically. If I open that up in the Gerber viewer, that is what you would get in your copper top layer, and you can see where all the parts to put everything is.
So this is what the PCB manufacturer needs to be able to make the different layers and everything else of the circuit board. You don't need to worry about it too much because it creates those all for you.
Exactly, yes. So, but we can go further than that. We can go to JLC PCB, which I'm just opening up. I don't know if you can see that.
No, we can't see it at the moment.
Okay.
Oh, there we are. Now we can see it. Yes,
Yeah.
that's fine.
So I would like to do this. You click on this Add Gerber file. So what you do is you find those files in the directory that you stored them. You put them into a zip file, and you add that Gerber file into there, and then you select what you want. So it will read the Gerber files, and it will work out the dimensions, how many you want, what sort of PCB thickness. So in this case, remember, it's 0.8 because we wanted those 50 ohm lines. Of course, we want it to be purple.
That's added a lot to the price there, I noticed, Mike. That went up
Yes.
from £1.64 to just under £15. So
Exactly.
keep it
Yes.
standard if you don't want to spend a lot more, I guess.
Indeed. So if you want it in a colour at 0.8 millimeters, it's going to cost you more.
And I believe, just for people wondering why that would be, it's because a most standard one will be green, and they make these circuit boards so cheaply. One of the reasons is, apart from it being in the Far East, is that they make it as one massive sheet every day, say, and then they cut it up for individual customers, isn't it? And they probably have to maybe do much smaller runs of other colours. Is that fair?
That's right. So if we go to the 1.6 millimeter, which is much more common, you see that's the same price. If I now select purple, it doesn't increase the price because they make a lot more of those.
Oh, I see. Okay.
Yeah. So it's only because it's 0.8
0.8
that there's a special process fee.
So they might have to put a special run on. Yeah.
Exactly. Yeah.
It's still a fraction of what it used to be, isn't it? When I was in business and buying circuit boards, prototypes cost an absolute fortune. You know, about £100 roughly for a panel.
Yeah. But look at this, £1.64.
Yeah, incredible.
You save that to the cart, and when you go to the shipping, you want to use the global shipping line. The whole thing will cost probably about a £5. So it's remarkably cheap, but you have to wait 2 or 3 weeks. If you want to get it fast, it costs you more. 24 hours costs you more, and if you want to get it by DHL, £20-30.
Yes,
You know, sometimes you need to do that.
Yeah.
So that's basically how you order a PCB.
Absolutely fantastic. Well,
Right. Now
we've
there's one
rushed
more
through
thing.
those things. I don't know. It's amazing that you've done that in an hour, really, shown us from nothing how to do it. Got a few little questions. We've got a couple from others, and also I've got a couple which I think are quite important. KiCAD, how much does it cost?
Nothing. It's free.
Wow. Okay. So it's
Donations, of course, if you want to donate.
Yeah.
I'm just going to.
Does it just work on Windows, or will it work on Mac and Linux, or?
It'll work on Linux. It'll work on Mac, but you're going to have trouble because you haven't got a right button. So I don't know what you do on a Mac when you haven't got a right button. It'll work on most types of.
Actually, if you use a
operating
Mac
system.
with a mouse with 2 buttons, it does work on a Mac, but I know they don't use it.
Ah,
as
yeah,
standard.
okay.
But thank
So
you for that. Now, I've got a question. I do want to get this in. Sorry, Mike, we
Okay.
are pushing for time now. So a quick question for you from Tim, M0KEP. Why use a fill zone instead of a 1.5 millimeter track for the 50 ohm lines?
Right, well that's easy. So that's the bill of materials, incidentally. If you come and look at this very closely, let me zoom right in. Can you see how that's rounded around that capacitor?
Yeah.
That should really be a fill zone. It doesn't matter there, but when we get to here, to the device, if that was rounded, it would get too close to the next pin.
Right. So that makes good
But
sense.
you can. It just doesn't look very nice, really. And there's specific advice as to how you should do, where you should put the wires and things around these devices to get the best performance out of them. They work to 6 to 8 gigahertz, but
Okay, that's brilliant.
We're
I
only
want to
interested
try
in
and get through
70.
these questions, and if I can. G4SAQ Russ says, is there a maximum board size for the free version, Mike?
well, I'm sure there is, but it wouldn't make any difference if you paid for it. How much memory have you got?
So they haven't got a limit because it's free, and then
No.
you have to pay if it's bigger, no?
No, I mean there's a maximum size that the PCB house could create, of course, and the number it does multiple layers. Incidentally, you don't just have to have 2 layers. You could have 3 layers, 10 layers, whatever. It does all of that.
Okay.
And you can have wires in between layers and in between internal layers, all the normal stuff that you get with a paid-for package It's very good actually, and it's been supported by CERN, which means it's got reasonable development capability.
Yeah, it's really good. And I see that just looking at doing a little bit of homework before your talk, you know, it even imports schematics from programs like Eagle, Altium, and CADStar. So if you use something else,
I've done that.
And I guess you could design your circuit from the first place on KiCAD then.
Oh yes,
Rather
that's what
than
I
have
normally
to
that's
redraw
what
it.
I normally do actually, because I find it easier to draw the schematic. And if you want to move, pins around and things, then that's very easy to do on KiCAD. It's a lot harder to do on a piece of paper because you have to start rubbing things out and
Yeah.
redrawing them and things.
Absolutely. And by the way, Noel G8GGZ has added on there that Mike designs the BATC PCBs and then emails him the Gerber files, and then he orders them in blue with DHL delivery from PCB Way. So that's how we get them quite quickly. Mike, thank you. Oh, I've got one other question. Julian Baldwin has asked, are there any other UK producers to avoid using the Far East? And well, I'll let you answer that.
Yes.
And but they cost quite a lot more, don't they?
Yes, they do.
Unfortunately.
Newbury Electronics used to be the one that we used professionally. I don't know if they still exist. I mean, the other thing is, if you want to get a board for, say, a satellite, I know that David MG0MRF does that when he's building CubeSats or FunCubes. You want to go to a proper professional PCB
Yes.
house with traceable
It
things.
is,
But
and
for just knocking something up for amateur use, these are very, very cheap.
I think I agree with you. I mean, it's and I'm as patriotic as others, and I try and buy British. And we used to buy British circuit boards for production, actually, from a company called Minitron in Kent, and they do offer a reasonably priced prototype service. However, it's still around £80-90, something like that, to buy one-offs. And if you're a hobbyist, that's probably a lot for just to try something out. So that's why these firms, they do come in. And the thing is also fair to say, Mike, as well, if you order quite a lot, then the price actually goes up, doesn't it? They do specialise in just producing small runs.
Yeah, they will do bigger runs, and it does work out cheaper. But usually it's a specialist. The other thing to note, by the way, is a lot of the Chinese houses have a size limit, and if it's more than 100 millimeters square, it costs more.
Yes,
They
quite a
add
lot.
$7 euro engineering fee or something.
Yeah.
So yeah, but I mean, I've had boards that have cost £4 delivered
Yes, extraordinary.
for five. It's ridiculously cheap.
Great. Mike, thank you very much indeed for today's talk and doing this live. As Michael EA7KIR says, it was extremely brave of you to do this live. And I echo that, and everybody does. I'm sure we all appreciate this.
Yeah.
I'm sure it's also, by the way, this is all going up on YouTube as well as the BATC line. So if you're watching on YouTube, or if you look afterwards, within a day or so, this will all be up there to replay. So if you are going to have a go at KiCAD and you haven't done so already, you'll better rewatch this on there. Mike, thank you ever so much for this demonstration. I'm sure it's inspired many of us to give circuit board design a go. I started way back in the late 70s and 80s, and at that time we were using red and blue tape on clear acetate to make circuit boards. So it's moved on quite a lot, and to think that this software is free is wonderful. Thank you ever so much.
We used to use pens, didn't we?
Oh yes, pens as well, absolutely. and crepe tape. My very first ones that I used to etch myself as a kid. Anyway, many thanks for your demonstration today, and also thanks for all the work that you do for designing circuit boards for the club.
Okay, thank you, David.
Thank you very much, Mike.